Debris flows comprise a complex mixture of soil, water, and large boulders, and are highly scale dependent. Both rigid reinforced concrete barriers and flexible steel net barriers are used to arrest debris flows. Flexible barriers are more advantageous since they blend in well with its surrounding environment. In this study, two-phase flows comprising viscous fluid and sand and bouldery flows consisting of glass beads were modeled. A storage container and a model slope and barrier are installed inside the model container. A new flexible barrier model was developed for the study. The new model consists of a rigid post with 4 cables. A net or membrane can be installed on the cables. The spring elements are responsible for controlling the load displacement behavior of each cable. The displacement is captured using laser sensors, while axial force is captured using load cells. A comparison of typical load displacement behavior of a prototype flexible barrier cable with the performance of the newly developed spring element is shown. The black data series shows the highly nonlinear prototype response of a real barrier cable. The red data series shows the spring element loaded under static conditions, and the green data series shows the performance of the spring element under dynamic loading conditions. This video shows a two-phase flow with 50% solid fraction impacting the model flexible barrier. As the flow impacts, the membrane deforms at the base of the barrier. The debris progressively runs up along the height of the barrier, and the membrane deforms accordingly. The run-up eventually cascades over the barrier. The flexible barrier model enables the load displacement of each cable to be captured. This provides an estimate of the energy absorption ratio, which is the ratio of the energy absorbed by the barrier to the flow energy before impact. Results reveal that flexible barriers only absorb up to 15% of the impact energy. The rest of the impact energy is dissipated by internal shearing of the granular assembly and viscous shearing of the fluid. This implies that it is over-conservative to use energy ratings for discrete rockfall events for flexible barriers designed to resist debris flows. This video shows a bouldery flow with a prototype particle diameter of 0.9 meters impacting the model rigid barrier. As the flow front impacts the barrier, a highly collisional flow behavior is observed. This graph shows the influence of varying particle sizes on the pressure coefficient. The black and red horizontal dashed lines show design recommendations for rigid and flexible barriers, respectively. For a rigid barrier test, the pressure coefficient increases with particle size. By contrast, a flexible barrier does not show a strong correlation between the pressure coefficient and particle size. Results show that design recommendations for rigid barriers fail to capture the impact pressure for normalized particle diameters greater than 0.6.